Hot on the heels of RTX 5000's announcement and hopefully release soon, I'm here in the Fontainebleau, or how do you pronounce this? I don't know. It's a hotel in Las Vegas, and I'm sitting down with Bryan Catanzaro, Vice President of Applied Deep Learning Research at Nvidia.
That's right.
That's right. And the last time we talked was a little over a year ago when Ray Reconstruction first came out. And now with RTX 5000, a new DLSS model, first time since 2020 that we're seeing such a big change in how things are done.
Yeah, it's exciting.
It's awesome. And let's hope we can learn a little bit more about it. But I guess my first question to you, now that we're all seated down and relaxed, would be why switch over to this new model, this transformer model exactly for super resolution specifically at the beginning?
Yeah. Well, we've been evolving the super resolution model now for about 5 or 6 years, and it gets increasingly challenging to make the model smarter when you're just trying to cram more and more intelligence into the same space, right? You have to innovate. You have to try something new, and the transformer architecture has been such a wonderful thing for language modeling, for image generation. All of the advances that we see today in things like ChatGPT or Stable Diffusion, these are all built on transformer models. And so transformer models have this great property that they're very scalable. You can train them on large amounts of data. And because they're able to direct attention around an image, it allows the model to make smarter choices about what's happening in the image and then also what to generate. And then we can train it on much more data, just get a smarter model, and then breakthrough results, where we're really excited about the kinds of image quality that we're able to achieve with our new Ray Reconstruction and super resolution models in DLSS 4.
Obviously, it's been in the lab for a while, and you've been looking at it. What are some key image characteristics that you're already seeing being improved with the new transform model in the super resolution modes, at least?
What the issues are with super resolution. It's things like stability, ghosting, and of course detail, right? And we're always trying to push on all of those dimensions, and they usually trade off. So as it's easier to get more detail if you accumulate more, but then that leads to ghosting. So there's this bias where it's like, oh, well, we want to get more detail, but we don't want to ghost, right? Or the opposite of ghosting, where you're having stability problems, where the model keeps, every frame it's making a different choice, and then you have like some thin geometry in the distance that's just like shimmering and flickering, so that's really bad also, right? So those are the standard problems with any sort of image reconstruction. And I think that the trade-offs that we're making in this space with our new super resolution and Ray Reconstruction models are just way better than what we've had in the past.
Do you also see great potential to advance? Because one of the things that's kind of been put out there is the old models we're seeing, they were hitting a wall in terms of quality that can be achieved with them. Do you see there's a greater trajectory up?
Yeah, absolutely. I mean, it's always been true in machine learning that a bigger model trained on more data is going to get better results if the data is high quality. And of course, with DLSS or any sort of real-time graphics algorithm, we have a strict compute budget that we're allowed to spend, only so many milliseconds per frame, right? And one of the reasons actually why we were brave enough to try building a transformer-based image reconstruction algorithm for super resolution and Ray Reconstruction is because we knew that Blackwell was going to have amazing tensor cores. Blackwell is designed as a neural rendering GPU. The amount of compute horsepower that's going into the tensor cores is going up exponentially, and so we have the opportunity to try something a little bit more ambitious, and that's what we've done.
You just mentioned it. I was going to ask later, but that specific performance, if I recall, DirectX super resolution on an RTX 4090 at 4K was sub half millisecond. I'm pretty sure by the end. Don't quote me there, but it was really low. And we look at the new transform model, not running on RTX 4000, but actually a ballpark difference in millisecond per frame that these models cost.
So the new super resolution model has 4 times more compute in it than the old one. Now, it doesn't take 4 times as long to execute, especially on Blackwell, because we have co-designed the algorithm along with the tensor core to make sure that we're running at really high efficiencies. So I can't quote the exact number of milliseconds on a 50 series card, but I can say that it's got 4 times more compute, and on Blackwell, we think it's the best way to play.
Okay, that's pretty great. Okay, Ray Reconstruction though. So last time we talked, it was really obvious to see that this is the direction that the industry should go in, because you can't just hand tune a denoiser for every single environmental setting, and the fact that we are trying to accumulate over time, you're just going to not be able to make those decisions. So it made a lot of sense. Really good progress in the beginning, but we already noticed problem points, as somewhat specific to titles, but there were some more universal ones too. So why exactly, based upon the preview I've seen, why is the transformer model actually improving these specific areas that we saw, for example, in Cyberpunk, like a specific one that we mentioned was skin?
Yeah.
Which was, it was bringing out more detail in the normal maps, but it was also kind of betraying the light scattering beneath the surface of skin.
Right.
Why exactly is the transformer model actually doing that better?
Yeah. Well, some of it's just polish. We've had another year to iterate on it, and we're always increasing the quality of our data sets. We're analyzing failure cases. We're adding those failure cases to our training sets, and then, our evaluation methodology. So we don't like how the skin looked either, and so we really, really wanted to make it better. So part of it is just general algorithmic development, but I think, the new model being much bigger and having much more compute in it, it just has more capacity to learn. It's more intelligent. And a lot of times when we have a failure in one of these DLSS models, that it looks in game like shimmering, ghosting, blurring, right? We consider those model failures. The model's just making a poor choice, right? It needs to be smarter. It needs to, for example, decide not to accumulate if that's going to lead to ghosting. It needs to, for example, not have a bias to make crenellated stair-step kinds of patterns on edges, right? Because it's like the whole point of anti-aliasing, you're not supposed to have that sort of stair-steppy thing, but due to a lot of technical reasons, we've been fighting that in DLSS for years. And I think these models are just smarter, so they fail less.
Yeah, that was one of my key takeaways. I've only really, as of the recording of this, I've only looked at B-roll footage that Rich had recorded of it. And one thing that it's not really a complaint, but it's something that you can sometimes see in AI, is that there is this a slight stylization of the output, I would describe it as, where things look painterly, like an oil painting.
Sure.
And that was one of the things that largely disappeared. In fact, I was not seeing it at all on my 4K set, which was one of the key things that I wanted to go away from Ray Reconstruction. So very happy to see that gone.
Me too, and I noticed in the B-roll that Rich was looking at animated textures, which have always really bothered me. And it's a really tricky thing for DLSS super resolution or Ray Reconstruction to deal with animated textures, because motion vectors from the game that are describing how things are moving around don't go along with the texture, right? It's just a television; it's just sitting there, and yet you don't want the screen on the TVs everywhere to just be blurring as stuff moves around. So that requires the model to kind of ignore the motion vectors that are coming from the game. The model has to basically analyze the scene and recognize oh, this area is actually a television with an animated texture on it. I'm going to make sure to not blur that. And it was really hard to teach the prior CNN models about that. We did our best, and we did make a lot of progress, but I feel like this new transformer model opens up a new space for us to solve these problems.
Yeah, and there's a lot more in that. I hope we get to at least do a more dedicated look at just specifically Ray Reconstruction, because I feel like that it had more to gain because it was so nascent technology.
Yeah. And
this is actually almost a larger leap than what we're seeing with SR, it feels like.
I think that's true.
But okay, so SR, Ray Reconstruction as well. But another part of this is FrameGen, which is now also changed again. That was actually the unexpected thing. I thought that would be rather static, but no, you guys are changing it. One of the big changes is now that optical flow is not being used, at least from the hardware side.
Correct.
Why? Why do that?
Well, because we get better results that way. Technology is always a function of the time in which it's built. And when we built DLSS 3 frame generation, we absolutely needed hardware acceleration to compute optical flow. We didn't have enough tensor cores, and we didn't have an optical flow algorithm that was good enough. We hadn't developed a real-time optical flow algorithm that ran on tensor cores that could fit our compute budget. And so we had the optical flow accelerator, which Nvidia had been building for years as an evolution of our video encoder technology, and also it's been a part of our automotive computer vision acceleration for self-driving cars, and so we have this technology, and it made sense for us to use that for DLSS 3 frame generation. But the difficult part about any sort of hardware implementation of an algorithm like optical flow is that it's really difficult to improve it. Like it is kind of what it is, and the failures that arose from that hardware optical flow, we couldn't undo them with a smarter neural network until we decided to just replace it and go with a fully AI-based solution. And so that's what we've done for frame generation in DLSS 4. Now, this new frame generation algorithm is significantly more tensor core heavy, and so there's still a lot of requirements on the hardware in order to run it. But it has a few good properties. One is it uses less memory, which is important. We're always trying to save every megabyte. Two is it has better image quality. And that's especially important for the 50 series multi-frame generation, because the percentage of time that a gamer is looking at generated frames is much higher. If you're alternating generated, rendered, it's like half the time you're looking at generated frames. But if you're doing 3 generated frames, then it's like 3/4 of the time you're looking at a generated frame. Artifacts are going to be much more visible. So we needed to make the image quality better. And then the third thing is we needed to make the algorithm cheaper to run, in terms of how many milliseconds it took, especially for the 50 series when we're doing multi-frame generation. What we wanted to do was make it possible to amortize a lot of the work over multiple frames that we're generating. Because if you think about it, there's really, 2 rendered frames that we're analyzing in order to create a series of frames in between those. And it seems like you should do that comparison once, and then you should do some other thing to generate each frame. And so that required a different algorithm.
Yeah. Keeping on that subject, though, of frame generation, now that it's running wholly on tensor cores, obviously it's a more intensive task as a result of that in some degree. What's keeping it then from running on RTX 3000?
I think this is primarily a question of optimization and also engineering and then the ultimate user experience. Mm-hmm. We're launching this frame generation, the best multi-frame generation technology with the 50 series. And we'll see what we're able to squeeze out of older hardware in the future.
That would be interesting. So another part of this, though, was frame pacing. Last time we talked about DLSS 3, I don't even remember when we talked about this, but I definitely remember just talking about it with you, that frame pacing has always actually been an extreme challenge because just, especially in a VRR scenario, what has changed with regards to frame pacing actually with DLSS 3 frame gen, or DLSS 4 frame gen?
Yeah. So we have an updated flip metering system in Blackwell that has much lower variability and takes the CPU out of the equation for deciding exactly when to present a frame. Mm-hmm. And because of that, we're able to reduce the displayed frame time variability by about a factor of 5 or 10 compared with our previous best frame pacing. And this is especially important for multi-frame generation because the more frames you're trying to show, the more the variability really starts throwing a wrench into the experience.
Yeah, if the base frame time is something like 4 milliseconds. It's very, just even one off frame will just ruin the entire presentation. That's why I'm very against frame time spikes, and I think it's something developers should look at. And it's good to see that FrameGen is actually putting in more. Rich already in his video pointed this out. I guess when we have full coverage, we'll be able to look at it more in depth. Especially, I'm very curious to see if since you mentioned it as a Blackwell specific feature, whether if we run the 2x mode, for example, on an RTX 4080 versus a 5080, whether we'll see differences.
Yeah.
You would think we would?
I expect that, DLSS 4 is just better than DLSS 3. So I expect that things will be better on 40 series as well.
Okay, that's pretty great. Now, one thing I've talked about also with you in the past was standard VSync support. Now, this is something that not a lot of gamers actually care about. This is actually totally a DF question. But most people are running...
I love DF viewers, though.
Yeah, it's all right. Most people are probably not running standard VSync these days. They are running G-Sync, VSync, whatever, VRR displays. But for our coverage, and always trying to cover these things, we need a good VSync presentation because we can't be showing frame tearing, that looks ugly. We need to accommodate YouTube, which is a 60 hertz, 60 FPS medium. Right now, DLSS 3, I would say, it supports VSync in its G-Sync mode, which is great. We don't get tearing above the monitor refresh rate. But it doesn't really explicitly support standard VSync for any titles. Like, why is that, and could that be at all changed? It would help DF workflow at least.
I'm not an expert on display technologies. I work mostly with the artificial intelligence side of DLSS. But my expectation is that these are engineering problems. My expectation is that if that was a priority for our customers, that we decided to go solve it, I'm pretty sure that we could solve that.
I imagine you could do, but I'm like that 1% that wants a standard VSync for some reason for my videos. But thank you for answering that. I guess another part of frame generation is now Reflex 2, though.
Yeah.
But it's different this time. It's not just a reduction on the PC side of latency. There is a generative AI aspect to this now. Could you talk a bit about it?
Yeah. So, I'm always thinking about real-time graphics in 3 dimensions. There's smoothness, there's responsiveness, and then there's image quality, which includes ray tracing and higher resolution and better textures, all that. With DLSS, we want to improve on all of those, right? And we're excited about Reflex 2 because it's a new tool, a new way of thinking about lowering latency. What we're doing is actually rendering the scene in the normal way, but then right before we go to finalize the image, we're going to sample the camera position again to see if during the time when the GPU has been rendering that frame, the user has moved the camera. And if that happens, then we're going to warp the image to the new camera position. And most of the time, for most of the pixels, that's actually going to look really good, and it's going to dramatically lower the latency between when you move the mouse and when the camera position moves, because you're going to feel like it's just much more immersive. The trick is, of course, that sometimes when the camera moves, there's something that is revealed that was hidden before, and we call that a disocclusion. You could also think of it as like a hole that, like, a pillar moved, or like the end of the gun moved, and you just kind of have a hole with no information about what should be there. And so that's the trick with a technique like Reflex 2, is how are we going to fill in those holes to make a convincing looking image. I think that the trade-offs that we've made with Reflex 2 are going to be really exciting for some gamers that are really, really latency sensitive. I think there's still more work to do to make the image quality even better, and you can imagine that AI has a big role to play here as well.
Yeah, it's interesting too, because the input latency is a matter of perception. Yeah. And this is playing completely with that, because on a technical level, it is not actually moving the real 3D scene. It is a 2D image manipulation of that, right? But it's playing with it so that you can appreciate it as if that were happening.
Yeah.
It's impressive. Pretty cool, actually, idea.
I think it's pretty fun. I mean, to me, it feels totally different. Playing a game with Reflex 2 just feels so much more connected. Of course, I'm going to be looking at the image quality artifacts that happen from this in-painting problem, right? Because that, like with Reflex 2, that's the real technical challenge is how do we fill in those disoccluded holes? And so I'm excited about Reflex 2. I think a lot of gamers are going to love it, especially in certain titles that are very latency sensitive. But DLSS, we're just trying to give gamers more options, so they can play how they want. If they want a lower latency, if they want to increase image quality, if they want smoothness over everything else, DLSS has something for everybody.
Yeah, the ability to choose 2, 3, 4, inserted frames there.
Yeah.
It's a big deal.
And you can do that in the NV app as well.
Very useful.
To override, because games, especially games that integrated frame generation before DLSS 4, they don't even have a UI for selecting 2, 3, or 4x. But rather than try to update all the UIs for all the games, we figured we could override it with NV app, and then gamers can choose what they'd like.
Coming into that multiple frame generation, though, when we talked about DLSS 3, there was a question of what is your lowest acceptable minimum input, real input frame rate? What would you say for a 3x or 4x mode?
I think that the acceptable input frame rate is still about the same for 3x or 4x as it was for 2x. I think the challenges really have to do with how large is the movement between two consecutive rendered frames. And when the movement gets very large, it becomes much harder to figure out what to do in between those frames. But if you're dividing that into smaller pieces, if you understand how an object is moving, dividing the motion into smaller pieces isn't actually that tricky, right? So the trick is figuring out how the objects are moving. And so that's kind of independent of how many frames we're generating.
Very true. Where do you see the future of frame generation? Because now it is kind of taking whatever raw performance you can give it and then blowing that up at a minor performance cost, at a minor input latency. But eventually we're going to have 1,000 hertz monitors, maybe even higher. Where does frame gen fit into that future of ultra high refresh?
Yeah. Well, I'm excited about 1,000 hertz monitors. I think that's going to feel amazing. So I definitely think that we're going to be using a lot of frame gen to get to 1,000 hertz. These days, I think graphics is shifting. AI. We've been on this journey of redefining graphics with neural rendering now for almost 7 years since RTX was released, right? And we're still just at the beginning. If we think about the approximations that we use for graphics, there's still a lot that we would like to get rid of. One really interesting thing that you brought up earlier is subsurface scattering. It's kind of crazy if you think about it that in 3D graphics today we're mostly simulating a 2D manifold, right? We're not actually doing 3D graphics. We're bouncing light off of pieces of paper, that are like origami heads or something, but we're not actually moving rays through three-dimensional objects. And most of the time, for opaque things, probably doesn't matter. But for a lot of things that are semi-translucent, a lot of the things that make the world feel real and textured, we actually do need to do a better job of working with light transport in 3 dimensions, like through materials. And so you ask yourself, what's the role of a polygon? If the job is to think about how light interacts through 3 dimensional objects, probably this model that we've been using for the past 50 years of let's really carefully model the outside surface of an object, that's probably not the right representation. And so this phenomenon that I think is happening is we're finding neural representations and neural rendering algorithms that are able to learn from real world data and from very expensive simulations that will never be real time. And then we're able to come up with technologies that are, I think, going to be much more realistic and much more convincing than we could ever do with, traditional, what I call bottom-up rendering. Bottom-up rendering, you're trying to model every fuzzy hair and every snowflake and every drop of water and every light photon so that we can simulate reality. At some point, we're making a shift away from this explicit bottom-up kind of graphics towards a more top-down generated graphics, where we learn, how do snowflakes look? And, for example, when a painter paints a scene, they're not actually simulating every photon and every facet of every piece of geometry. They know what it's supposed to look like. And so I think neural rendering is moving in that direction. And I'm very excited about the prospects of overcoming a lot of the limitations of today's graphics, which I think are really difficult to scale. The more fidelity we put in bottom-up simulation, the more work we have to do to capture textures and geometry and then animate it. It becomes very expensive and really, really challenging. There's a lot of graphics that's really held back because we just don't have the artist bandwidth. We don't have the time or the storage to really save all of that. But okay, so we're going to have neural materials, and we're going to have neural rendering algorithms, neural radiance caches. We're going to find ways of using AI in order to understand how the world should be drawn, and that's going to open up, I think, a lot of new possibilities to make games more interesting looking and more fun.
Yeah, that's one of the things that I've always lamented about polygon-based graphics is the inability to represent anything like heterogeneous volumes and stuff.
Yeah.
And we've got nothing for that. And ray tracing that is almost impossible for real time. So I'm happy that neural rendering is going to start bridging that gap. And for more complex, deformable materials, fluid simulations, all these things. So that's what I hope where the future goes to.
That's where we're headed for sure.
Well, I think that's actually all my questions regarding all the neural rendering and DLSS and frame gen and all that. Maybe I could have come up with more, but hey, this is done live.
Well, it's an honor to speak with you. I'm a huge Digital Foundry fan, so
thank you so much.
Just love the work you guys do.
Well, Bryan, thank you so much for talking to me today.
Yeah,
and,
of course.
If you did like this video interview for Digital Foundry, well, hit that like button, subscribe to the channel, hit that little bell button in the corner to get informed as soon as Digital Foundry posts a video. And support us on Patreon to make stuff like this possible. And as always, this is Alex saying, well, auf Wiedersehen.